This is a discussion of problem number 2 from section 3.4. It was not one of the assigned homework problems, but it's very similar to number 1, so I thought this would be a good example so you would feel more comfortable with number 1. We're not told what the matrix B is, but we're told that it has a complex eigenvalue and a complex eigenvector. If you have a complex eigenvalue, you will, of course, have a complex eigenvector. You're asked to find the general solution of the differential equation that has as its constant coefficient matrix B. Well, as was shown in class, a function of this form will solve this linear system. However, this is a complex valued function. Lambda is complex and V is complex, and so the solution will be complex. However, Euler's formula will allow us to rewrite it in a form where we can separate the real and imaginary parts, and it's a fact that both if the complex valued function is a solution of this linear system, then its real part is also a solution and its imaginary part is also a solution. And I will demonstrate that in another screencast. Anyway, the mechanics of getting to our solution is first to rewrite e to the lambda t in our complex eigenvalue v. We separate our real part and our imaginary part in the exponent. We write this as e to the minus 2t times e to the 5ti. This is the term that Euler's formula applies to. E to the 5ti, coming up here, according to Euler's formula, can be written as cosine of 5t plus I sine of 5t. And we still have the e to the minus 2t sitting out front. This is being multiplied by our eigenvector. And you can think of this in a way as a scalar. This it's a complex number, but this term multiplies both components of this vector. When we multiply the 1, we just get cosine 5t plus I sine 5t back again. When we multiply this times the complex number 4 minus 3i, we have to do some foiling. So we're going to multiply the cosine times the 4 to get a 4 cosine 5t. When we multiply the sine, the I sine, times this imaginary part, we also get a real term. And since I times I is minus 1, we get a positive 3 sine 5t. And my goal here is to organize the real components together and then group together the complex components, the imaginary components, I'm sorry. So this is our real part. And then when the I sine 5t multiplies the 4, I see I've made a little mistake there. I'm missing a 4 here. So when the this imaginary term multiplies this real part, we get a 4 sine 5t with an I in front of it. And when cosine 5t multiplies the minus 3i, we get a minus 3 cosine 5t with an I in front of it. And I'm sorry, this is a little, I ran out of space, it's a little crowded in there, but here I'll separate. These two terms are real, have no imaginary part, and so dividing this big vector into two parts, into a real part and an imaginary part, I've got my cosine 5t plus, I've got my cosine 5t as a real part, and I've got my 4 cosine 5t and 3 sine 5t, 4 cosine 5t plus 3 sine 5t as my real part. Added to that, the things that have the imaginary part, so I times e to the minus 2t, and here again I need to be careful. I have a sine of 5t, that is correct, but I am missing the number 4 right here. And so minus 3 cosine 5t plus 4 sine 5t is the imaginary part. So, as was stated and as I will demonstrate in a separate screencast, the real part of y, namely these two terms, namely this vector, is a solution, as is the imaginary part. And once again, I need to squeeze in the number 4 right there, this is also a solution. We also observe that at time 0, y1 is a 1 and a 4, sine of 0 is 0. And y2 at time 0 is a 0 and a minus 3, and the sine of 0 is 0. These two terms are linearly independent, and so we have two solutions of a linear system whose initial values are linearly independent, and therefore the general solution is simply k1 times y1 plus k2 times y2. No reason to rewrite these things. They're too complicated or too cumbersome. This is a perfectly good expression for the general solution as long as we've stated clearly what y1 and y2 are. Okay, I hope that's a good problem to help you look at question number 1. Good luck.